workshop on computer-aided drug design. In the previous two sessions, Professor Mukesh Doble discussed about the ADME property predictions, pharmacophore, ligand-based designs, and he also discussed the various softwares that are useful to the drug design. A kind request to the participants to mute their audio and video during the session. The participants can ask their queries and clear their doubts once the session gets over, and unnecessary chat should be avoided in the chat box. Now the session will take over by Professor Mukesh Doble. Sir?
Hello, good morning to everybody. Um, we have been talking about the computer-aided drug design past 2 days. So first day we looked at the various structural features, ADME properties, drug likeness property, various rules for identifying drug likeness property. So I showed you many softwares. I showed you some databases also. Yesterday we looked at ligand-based design. Ligand means drug, small molecule. Unlike the target-based design, where it's the protein or target enzyme or whatever is a macromolecule. So yesterday we talked about ligand-based design. There we talked about pharmacophore-based approach. Okay, in pharmacophore-based approach, we look at some of the molecules which have been reported for some activity. It could be in molecules for inflammatory towards an enzyme or anti-cancer towards a particular target. Then we try to find out what are the common features, pharmacophore features, which are common to the molecule. So the molecules are superimposed in 3D, and the features like hydrophobic groups, aromatic groups, hydrogen bond donors, that means OH or NH, hydrogen bond acceptors, that means N or O, cations, anions are identified. So it tries to identify what are the common features. So the logic is, if those molecules have certain common features and they exhibit an activity, if I go to some databases and look for molecules with similar features, hopefully they also will have those activities. So that way we can come up with new structures which has not been reported. And of course, once we pick up those molecules, we have to look for the drug likeness property using different software I talked about. So yesterday I showed you the one which is called PharmaGist. PharmaGist does the identification of the pharmacophore. So there we give a zip file containing all the molecules which we want to put in .mol2, mol2 format. So I also showed how to get mol2 format. You go to Zinc database, get the structure in SDF format, use OpenBabel, convert them into mol2 format. Okay, convert them into mol2 format, and then put them all into zip file, run PharmaGist. So PharmaGist picks up the common pharmacophore features. Okay, only these are called the pharmacophore features: hydrophobic, aromatic, donors, acceptors, and any anions, cations. We can view that features using PyMol. Again, PyMol is a free software we can download, and we can get a license as a student or as a faculty. Now we can search the Zinc database or any other database using these features. That program is called a Zinc Farmer. Yesterday I showed you that. So it picks up molecules which are having similar pharmacophore features with the same distances. I also showed you distances, how to get the distances in PyMol. So it picks up, and then based on lowest RMSD, it arranges them in that order. Then we can look at each of the molecule and run Swiss ADME or pre-ADMET software to find out whether they satisfy all the conditions. If not, you reject that, take another molecule. Like that, you can build up a set of molecules which have the same pharmacophore features as well as the satisfying the ADME and drug likeness property. Then as an organic chemist or a medicinal chemist, you can synthesize those molecules go to the lab, and then test their activity. So this is the entire workflow, how it works. Okay, so if the structure is available in Zinc database or any other database, we can download the SDF file. But what happens if it is not available? For example, you might have come up with something totally new molecule. Maybe you have got it from some natural source, natural product, phytochemical, or some marine organism. So we use something called the Marbrain Sketch. That also is a free software. We can get the license as a student or a faculty. So there we can draw the structure, and then we can get the three-dimensional minimum energy confirmation of the molecule. I am saying minimum energy because molecules will attain a three-dimensional confirmation, so that the energy is minimum. That's the thermodynamically stable state. Okay, so if I don't have structures, I can go to Marvin and then draw the structure and then minimize energy, and then I can get the SDF file, and then I can go ahead to get the pharmacophore modeling. So that's the entire workflow of pharmacophore based design. Now let's look at another ligand based approach that's called QSAR, quantitative structure activity relation. So this is a quantitative measure, structure activity. So you are relating the structural descriptors or structural features with the activity, but here you have a mathematical equation. Unlike in pharmacophore modeling, we just looked at what features are there. Okay, for example, what type of whether all the structures have hydrogen bond donors or acceptors. Like I showed you yesterday in one example, all the molecules had 3 acceptors at some 8 angstroms, 1.5 angstroms, 1.3 angstroms distance. Okay, so there we just look at the features. That's pharmacophore. Here we develop a quantitative structure activity relation. So we develop a mathematical equation where activity equal to some descriptor or structural feature, okay, on the right hand side. So left hand side could be activity, right hand side could be descriptors or features. So we get a quantitative structure activity relation. Okay, so what's the use of quantitative relation? The advantage is if I have a relation, tomorrow I come up with a new structure, I don't know its activity, I can get the structural descriptors using your Swiss ADME or pre-ADME or ChemDes, and then put it in the equation, and I can predict what will be its activity. Okay, that's the left hand side. Okay, so in pharmacophore modeling we can't predict the activity, but here in QSAR we can predict the activity. Okay, so this QSAR is slightly more tougher in the sense I should initially have some molecules reported for some activity, and the activity value should be known. Okay, so if I am looking at an enzyme in the inflammatory pathway, prostaglandin inflammatory pathway like cyclooxygenase 2, I know some 10 molecules which is inhibiting that enzyme. I know their numbers, activity numbers. Then I can use it for developing a QSAR. So I need to know the experimental numbers to start with. Okay. Then I develop a QSAR, then I can predict what will be the activity of some new molecule. That's what QSAR does. So QSAR can give a quantitative activity prediction. That's the advantage of QSAR, but I should already have some activity numbers for some known molecules to start with. Okay, so we will look at QSAR. There are 2 types of QSAR, 2D and 3D. We will stick to only one 2D type of QSAR. Okay, so today we will talk about that. We'll look at how the equations are developed and any softwares that are available and so on. Okay, so QSAR is nothing but quantitative structure activity relationship. So it's quantitative. So you have a number. So left hand side, this is like regression equation. You must have all studied in 10th and 11th regression. Y equal to mx plus c. So y could be your activity, x could be your structural descriptor or structural feature. Y equal to mx plus c means I am saying only x, only one descriptor. You can have y equal to m1 x1 plus m2 x2 plus m3 x3, like that, you know. So there will be many descriptors also possible on the right hand side. left hand side will be your y, that is the activity. So this is exactly like regression. So it's like y equal to m1x1 plus m2x2 plus m3x3 and so on actually. Okay, so for example, activity is equal to a plus descriptor 1 plus c plus descriptor 2 and so on. So it's like a regression relationship. You can even have square terms. Just like y equal to mx plus c, we can also have y equal to mx square plus m2x. So we can also have square terms. So it depends on how many data points we have. There are some rules. I'll talk about it later. How many data points you should require. This is all coming from statistics regression. So you have to recall your studies which you have done in your school or maybe in the first year statistics course, regression course. So QSR is like regression. It's a quantitative structure activity relationship. So you start with some set of compounds whose activity is already reported. So you go to literature, get some, even for pharmacophore, we have to go to literature, get some structures of compounds which are known for some activity. Here we also should have the activity values also, okay, because we are doing a quantitative. So we get some compounds list whose activity is reported, say for enzyme like cyclooxygenase 2 or from ACE2, for example. So I know the activity value, okay. Then I calculate the descriptors for those molecules. I showed you ChemDes, I showed you SwissADME, I showed you pre-ADMET, so many softwares that are OChem. So descriptors can be calculated, okay. Then I develop y equal to mx plus c, like, or y equal to m1x1 plus m2x2 plus m3x3 plus c, like that, you know. So the x's are the descriptors. So we can't make very big equation. It depends on the number of data points I have, okay. So if the data points are very less, I will have only one descriptor model, that is y equal to m descriptor 1 plus c, or y equal to mx plus c. Even in statistics, we can't develop very complicated model if we have very little data points, because that depends on the degrees of freedom. Okay, so depending upon the number of data points only, we can have many descriptor model or single descriptor model and so on. So you end up with activity is equal to a plus b descriptor 1 plus b, c descriptor 2, like that, you know, model. What is the use of this equation? Like I said, I can use it for prediction, okay. If I have a new molecule, I think of, I don't know its activity value, I can calculate the descriptors of those molecules, put that in that equation, QSAR equation which I have developed, and I can predict the activity. So that's the advantage. So I can predict activity of new unknown molecules if I have a QSAR equation. That's one advantage. Other advantage, suppose I have some 50 molecules which I feel they may be good. Okay, I don't want to go to the wet lab and check the activity for all 50 molecules. So if I have a QSAR equation already, okay, then I can predict the activity of all the 50, and then see which the top 10 which shows very good activity. Okay, and the rest of the bottom 40 I can neglect. Then I can take the top 10 and go to my wet lab and start synthesizing those 10 molecules and then measuring their activity experimentally. So I can use it for screening. So I have too many molecules which I think are promising candidates, but I don't want to synthesize all those 50 molecules, then check the activity, which is going to be taking long time. So if I have a QSAR equation, I can predict the activity for all the 50, and then I could take the top 10 or top 15, which you think is good, and then go to the wet lab and synthesize those molecules. So that's screening. So I can use QSAR for predicting activity. I can use it for screening structures and selecting the best molecules which may have possibly the best activity. So that's the advantage of QSAR. Okay, so you can see the difference between pharmacophore based approach and QSAR based approach. Both are ligand based things. Both of them are looking at descriptors or structural features. Okay, here in QSAR we get a mathematical relation, y equal to mx plus c type. Y is your activity. In pharmacophore, we don't get mathematical relation, but we just identify the important structural features or pharmacophores necessary for certain activity. Okay, so let's go forward and see how to develop this QSAR. So in QSAR, I need to already have some known structures and experimentally known their corresponding activities. Okay, then I calculate the descriptors using different softwares. Okay, large number of descriptors. Like I said, we can calculate thousands and thousands of descriptors using these softwares. ChemDesk can calculate 1,800 descriptors. Swiss ADME can calculate. OChem can calculate another 50, 60 descriptors, and so on. Actually, okay. So like for human being, we have descriptors like length, height, and weight, and length of the arm. So those are the descriptors. Similarly, for molecules also, we can calculate thousands and thousands of descriptors. Okay, so different types of descriptors are there. They are called geometric descriptors, quantum chemical descriptors, electrostatic descriptors, thermodynamic descriptors. Geometrical means shape, 3D structure, shape, okay, volume of the molecule, then polar surface area, non-polar surface area, how many gaps it has got, okay, then number of carbon atoms, nitrogen atoms, so many things. They are called geometric descriptors. Then we have quantum chemical descriptors, okay, various quantum chemical parameters of the molecule, okay, electron interactions, electron-proton interactions, proton energies, those are called binding energies. Those are called quantum chemical descriptors. Then comes electrostatic, charge distribution, maximum charge, minimum charge, electrostatic charge, all those. Then comes thermodynamics, the delta G values, delta S values, delta H values. Then we have log P, log S, so many descriptors we can have. Okay, so descriptors, that's how you calculate descriptors for a given molecule. And as I said, these softwares can do lots of these descriptor calculations. We don't know which descriptor will fit the activity, but we calculate and then see which descriptors later on using some regression or statistical based method. Okay, for example, we know height of the person will correlate with a good basketball player because we already know. But in some cases, we might not know which will correlate with activity. So similarly, we will know the maybe the weight of the person may correlate with his weight lifting capacity. Okay, so we can say that descriptor will correlate with that. So in some cases we can say, but in many cases we cannot say. For example, if I want to know the IQ of the person, is there a descriptor which can tell what is the IQ of the person? It's very difficult. Can I say the size of his head or her head will match IQ? No. So what descriptor can we say? Is it the color of the hair which tells the IQ of the person? So we cannot say which descriptor will match with IQ. So that the problem is also there in QSAR, and in some cases, many cases, we can find out which descriptor can match with certain activity, or which descriptors describe the activity. But in some cases, we will not know which descriptors is needed for describing the activity. That problem can happen. Like I said, height will nicely correlate with basketball player, or weight will correlate with the weightlifting capability, and so on. But some things we will not be able to correlate. Okay. So what we do is we calculate many descriptors, and then we see which descriptors correlate with the activity, and then select the descriptor and develop a QSAR. That's what we do. Okay, I will show you a very simple problem. Imagine I have 5 molecules, 1, 2, 3, 4, 5. I checked for some activity. Okay, maybe anti-cancer activity. These are the 5 activities, anti-cancer activities. Okay, why? Okay, I calculated, say, 3 descriptors for these 5 molecules using Swiss ADME. Like you can calculate volume, log P, dipole moment, like that. Okay, so 5 molecules, I know their activity. and I know I have 3 descriptor values for these 5 molecules calculated. I can calculate many descriptors, but to start with, I am going to show you a simple situation. Okay. So I have 3 descriptors for these 5 molecules, and I have 5 activities. So you can solve these in Excel also. So I'll go to Excel. Um, okay, so okay, so we have these 5 molecules, 5 activities are there. Those are the Y's. Okay, in statistics we call them as dependent variable, and these are the descriptors which will come on the right hand side of the regression equation. We call them X's or independent variable. Please recall your old statistics. Okay, so the X's are called the independent variable, the Y's are called the dependent. Y is called the dependent variable. Okay. Okay, so I have copied them 2.34. Okay. All the activities, all the Y's are put here. You can see here, all the volumes are put here, log P's are put here, dipole moments are put here. You can see that by the data point. So how did I calculate the descriptor? I went to Swiss ADME like software and then calculated. I'm picking up just 3 descriptors, but you, as I said, you can calculate thousands of descriptors possible. Activities are known from my experimental data. Okay, activities are known from the experimental data. So the these are called the X's. In statistics, these are called the X's, and activity is called the Y. Y is the dependent variable. X's are called independent variable. Okay. We want to find out which one I can choose. X I can choose to develop my activity model. Okay, there is a formula in Excel. It's called a correlation. Okay, that is, it can develop, it can calculate a correlation coefficient. In this case, between volume and activity. Okay, you can see here. I am trying to read out the correlation between volume and activity. Excel has this function correl. Okay, so the correlation between volume and activity is 0.95, which is very good. If you remember, correlation coefficient lies between -1 to +1. So closer to 0 means it's a poor correlation. Closer to 1 or -1 means high correlation. Okay, if it is closer in the positive side, it means as the X increases, Y also increases. If it is closer in the negative side, as X increases, Y decreases. Okay, so here you can see the volume and activity are highly correlated, closer to 1.95. Okay, this is positive. So as the volume increases, activity also increases. Okay, now let us look at log P and activity. This is not good. 0.38 below average. Actually, anything 0.7 onwards is good, but this is below average, because we already have a very good correlation between volume and activity. And now let's look at volume and dipole moment. If you remember what is dipole moment is okay, it acts like a magnet. For example, if you take water, H2O, okay, the oxygen, because the angle between hydrogen, oxygen, hydrogen is 120 degrees, so it forms like a small magnet, so it creates a dipole. Okay, Okay, so dipole moment is what that is. Okay, so let us look at the dipole moment versus activity. So the command here I used is Corel, which is there in Excel. Okay, this is also very good. 0.94, this is negative. That means this is also very good. As the dipole moment increases, activity increases, or if the dipole moment decreases, activity will increase. So these two descriptors seem to correlate very well with activity. So as volume increases, activity increases with very good correlation coefficient. The other one is as dipole moment decreases, activity increases. So that's also a very good correlation. We can plot them and see also. We can plot the whole thing, each one of them. So you can see here, as the volume increases, activity increases. Very good correlation. We can draw a straight line. It's called add trend line. Display equation chart, display R square. Okay. Okay, so it's added a straight line. Okay, this is the equation y equal to. I hope you can all see this. So this is equal to y is equal to, okay, 0.0117x minus 2.027. So as the volume increases on the x-axis, the activity also increases. Okay, and the fit is also very good. This is called the R square. R square is a term that comes in regression. If you recall your regression studies in your school, you'll remember. So it's a very good equation. So this is the QSIR for this particular system, relating activity with volume, relating volume with activity. So volume is your independent variable x, or the descriptor, and the activity is the dependent variable y, or okay, which is on the left hand side. So your volume is on the right hand side, and your activity is on the left hand side. Okay, so this is called a QSAR. Okay, this is called a QSAR. So we can have like activity is equal to 0.0117 volume, okay, my 2.0254. Understand? So this is a QSAR relating activity and volume. Okay, now because we already know it will be a good relation, because we got the correlation coefficient as 0.959. But this one won't be a good relation, right? Because it is not very good. The correlation coefficient is not very good. Okay, so that won't be a good relation, but we can also see that. No problem. I'm relating log p, and that's my x, or the descriptor, or the independent variable, against activity, which is the dependent variable, or which is the y. So as you can see, this is not good. This is log P on the x-axis, activity on the y-axis. It's very bad. Okay, which was obvious before also when we look at the correlation coefficient was only 0.38. Whereas if you look at the volume relation, it's very good. No, as a nice equation, nice straight line, a good R square, we get it. So we also knew it from our original R value also. So as the volume increases, activity increases, and this is the QSAR equation. Here X is the volume, Y is the activity. So whereas if you look at our second log P relation, it's quite bad. It's all over the place as the log P changes. It's all over the place. And anyway, we will know that also when we got the correlation coefficient here, which is only 0.38. Okay, let's look at the third one. That is the dipole. Okay, that's the dipole. This dipole is the independent variable or x, and your activity is the dependent variable or the y. And this also should be good, but negatively correlated because the correlation coefficient is very good. Okay, on the negative side. Okay, so you can see that, and this also is very good. Okay, so as the dipole increases, activity goes up, or if as the dipole decreases, activity goes up. And this also is a very nice straight line. Just like this, we will draw that straight line because as you know, the correlation coefficient also was very, very good, minus 0.94. So we can draw the trend line, add trend line. Okay, this is the QSAR. If I use dipole, okay, y equal to minus mx plus c. Your x here is dipole. That's here axis. Y is the activity. That is this axis. R square is also very good. 0.88. Okay, this R square is better. That is the volume related equation. This is also not a bad model, good model. This is also a very good model. So I have two QSR equations. One equation relating log P, another equation relating dipole moment. For the dipole moment, activity will go up if I reduce dipole. In the volume equation, if I increase volume, activity goes up. So I can select both, any one of them, because both are reasonably good. But if I want to be really picky, I can select this volume relation because R square is very good, 0.92. So here y is the activity, x is my volume. So as the volume increases, activity increases. So this is the equation. Okay, it's going up. So this with the for simple problems, one we call it one. These are one descriptor models. For simple one descriptor model, we can use Excel itself. Excel can do even small other problems also. We'll not go into that as of now. So for a one descriptor model, these are very good. So what's the use of this equation? So if I have a new molecule, okay, if I have a new molecule, and that is new molecule, as a drug discovery scientist, you think these molecules will work. I don't know the activity. I have to go to my wet lab to determine activity. So what I can do, I can calculate the volume of that molecule using any of these softwares, Swiss ADME, and then I will put it in this equation, y equal to 0.0117x minus this. So I'll put the volume here, and I can predict what will be the activity. If the what activity is not as high as this, then I will say, okay, why should I bother about that molecule? If the activity looks better than this, then yes, that could be a possible candidate. So I can go to wet lab. So instead of considering taking all molecules to wet lab, which could be time consuming and resource utilizing, we could select molecules based on this QSAR equation. So that's the advantage. So if I have 20 molecules which you think possibly good candidates, what we can do, we can calculate volume of all those 20 molecules and substitute in this equation. I will get 20 activities, and then I could select top 5 which looks much better, and then I can take those 5, go to my wet lab, synthesize those molecules, and so on actually. So that's the main advantage of this QSAR equation. It can predict activity of new unknown molecules. Okay, so that's the main advantage of QSAR. Of course, we can also use dipole also. If I know the dipole, again, dipole can be calculated using this software. I can use this QSAR equation where here X is the dipole and Y is the activity, and also try to predict the activity. But in this case, this equation is better than this equation because here R square is 0.92, where the other one R square is 0.88, so slightly lesser. So like I said, closer to 1 is the best, but it's very difficult in experimental situations. We have a lot of errors coming in, experimental error. If you are doing cell-based studies, there is going to be a lot of error. Even bacterial study, so many errors can crop in. So this is a theoretical example which I am showing. So you are not going to have such fantastic R square. You will end up with 0.6, 0.7 type of R square. If you get 0.9, then I'm sure it is not true, because bacterial systems, there will be a lot of error coming in, and cell-based systems, you will not get 0.9 type of R square. By comparing the R square of different QSAR equation, we can select the one which looks good. Or by comparing the correlation coefficient, we can select the best descriptor. For example, in these 3, I would say volume correlates the best with activity. So I will take volume as my descriptor for generating my QSAR. So here my QSAR is Y is equal to 0.0117 X minus 2 point, like that. Okay, so X is my volume. So that's how we can shortlist descriptors. So if I have many descriptors, I can do a correlation analysis of all the descriptors with my activity, and then I can say, okay, this descriptor looks the best, so I will use that descriptor from my model. Okay, now I have 5 data points. Can I make a model like Y equal to, activity equal to M1 into volume plus M2 into dipole plus C? With 5 data points, it's not a good idea to do 2 descriptor model. Okay, it's good with 5 data points. It's good to stop with 1 descriptor model only. Okay, it's not a good idea to do with 2 descriptor model. If you have about 8 to 10 points, then maybe you can go with 2 descriptor model. So these are all some rules of thumbs. I will talk a little bit later, but with 5 data points, don't go for 2 descriptor model. You can get a model, but based on degrees of freedom, it's always good to have 1 descriptor model. That means like Y activity equal to M into volume plus C, or activity equal to M into dipole plus C. So I don't suggest Y equal to M1 volume plus M2 dipole plus C. That is a 2 descriptor model. Understand? So that's not a good idea. It's good if you have 8 to 10 data points. So more number of data points, we can have more longer set of descriptor models. But less number of data points, have less number of descriptor based models. There are many rules. I will show you later on. Okay, so with the Excel also we can do these type of interesting studies of getting QSAR for single descriptors. Okay, now the main challenge is we need to have experimental values for the activity from literature. So that could be the challenge. So getting lot of data points, experimental data points, could be very difficult. For example, I am looking at ACE2 inhibitors. Okay, angiotensin converting to enzyme inhibitors. So I need to have many experimental data points of reported inhibitors, either PIC50 or percentage inhibition or AD50, some value for all the molecules against H2. So you might not get so many, you may get only few. You may get eight data points or 10 data points. You might not get many. So you may end up with one descriptor model or two descriptors model and so on. Whereas if it's a very old disease, you may have many data points. Some bacterial infections, you may have 40, 50 data points. But if you're looking at some recent infectious diseases, you might not have so many experimental data points with different molecules. Okay? So that's the biggest challenge in getting experimental data points of activity. So here, as I mentioned, we need to have experimental activity data points. Okay, we can also use, there is one software, very simple software, which is available for developing QSAR. It's called Build QSAR. Okay, it's a free software. We can download that. I will show you how to do this. Sometimes this software has compatibility problems. But this software also can do one descriptor model, two descriptor model, many descriptor model, and then it can draw graphs, everything. So that's the main advantage. So this is the thing I had already saved the 5 data points. Okay, so I have already saved the 5 data points. Okay, so you can see this same problem of ours. Okay, so the volumes are given, activity is given in yellow, volume, log P, dipole, they're all given. So I saved it. So you can also build, it's called build QSAR. So we can have, if I have more molecules, it will come rows 6, 7, 8, 9, 10, 11, that. If you have more descriptors, you will have more columns here on top. Okay, so this can do a lot of nice things. I'll show you. This is called correlation matrix. So correlation matrix. Okay, so it has done a correlation between, I hope you can see this. It has done a correlation between descriptors themselves as well as with the activity. Okay, so it has correlated activity as a activity. So that is this diagonal is 1, 1, 1, 1 like that, and then it gives activity versus volume, just like we got it in Excel when we used correl function. So activity versus volume is 0.959. Activity versus log P is much less. Okay, it's called correlation matrix. Activity of dipole again is very good. Okay, you can see here activity versus dipole. And then it also does between descriptors also, volume versus log P, volume versus dipole, and so on. Okay, so between descriptors also we would like to have, because in statistics, when you look at regression theories, if you have two descriptors like x1, x2, or two independent variables, those independent variables should not be cross-correlated. That is what the regression theory says. Okay, so we should not have descriptors which are cross-correlated with each other. For example, if I am going to have a descriptor volume, and I also going to have another descriptor surface area in my model, chances are volume and surface area will be correlated with each other, because a big surface area means volume must be higher. Okay, so normally we should not use models like that. For example, if you take weight of a person and height, chances are tall persons could be heavier. So there could be a correlation between height and weight also. So we should not have a model where the height as well as weight comes as the independent variable. So the independent variable should not be cross-correlated, it's called. So that comes in regression. So this gives that data also. Okay, for example, actually, if you see volume and dipole are correlated also. So we should not have, if I am planning a two descriptor model, I should not have volume and dipole as my x's or independent variables. Okay, that's what it means actually. whereas volume and log P are not correlated. So I can have that sort of model. So cross correlation between X's is an important knowledge we should have when we develop multiple descriptor QSAR model. When you are developing single descriptor QSAR model, it does not matter. But when you are developing multiple QSAR model, the X's should not be cross correlated. Okay, that's the usefulness of that. Then we go to, it can plot variables. Okay, so it has plotted, as you can see. So one click it does this. In Excel, I had to do many clicks. So volume versus activity. So there also we saw, you remember? Volume versus activity, same thing it's doing. Okay, volume versus activity here. Okay, this graph, same thing it's doing, but one click it gives you, and it gives you a lot of information. If you remember your analysis of variance statistics, it gives you F value, all those things also. So this x-axis is volume, y-axis is activity. So instead of volume, I can make it log P. So as you know, log P was very bad, right? If you remember in your Excel also, log P was very bad. This is the log P, the left-hand side graph. Same thing it is showing also. Log P is bad. When you do the dipole, it is negatively correlated. So as dipole increases, activity goes down. As dipole decreases, so same thing we saw it in your Excel also. If you remember this graph, last graph, so same thing it does, but it does it in one click. It gives you a lot of statistical information. Also, that's the beauty of this software. Okay. Correlation, and then it can also fit the equation, multiple linear regression, it can say. So here we can pick one descriptor model, we can pick two descriptor model. Okay, so it has picked up one descriptor model here. Activity is equal to something, volume minus something. So it gives a lot of statistics. It's called Q square, press, predicted sum of squares of error. So you need to have brush up statistics and regression. There are different types of statistics called R square, adjusted R square, predicted R square, Q square, cross-validated Q square, bootstrap Q square. So many different types of statistics are there. So you need to brush up to see how good the model. All these tells you how good the model prediction is. So one descriptor model, it is given. Okay, so instead of log P, sorry, then I can dipole also. So it gives you one descriptor model here. You can see here activity is equal to negative. Okay, dipole. It also gives you the predicted values, standard deviation, actual values. So all those things. We can also, although it's not a good idea to do a two descriptor model, we can also do a two descriptor model with volume and dipole. It's not a good idea with 5 data points, but I just want to show you two descriptor model. Okay, so it has given activity is equal to something into volume plus something into dipole plus a constant. So this is a two, then all the statistics is there. I can see here. So this is giving a two descriptor model. Activity is equal to descriptor 1 is your volume, descriptor 2 is your dipole. So although with 5 data points, it's not a very good idea to go for a two descriptor model. If you have 8 data points, it's okay. You can go for a two descriptor model, but not a 5 data points. So this can do nicely all these with one click. Okay, then if I have more data points, I can make even 3 descriptor models. Okay, so I don't know whether it will work. 3 plus 1, 4, 1 degree of freedom. Okay, so degrees of freedom will be very bad. So I have given all the 3 descriptors, so it comes up. So it will do, but as a person who knows statistics, we should not do these type of modules at all. But you can make 3 descriptors also in this. So this equation, activity is equal to something into volume plus something into log P plus something into okay, dipole, like that. So if you had more data points, then this equation will make sense. But with the less number of data points, I would not go for this. Okay, so this build QSAR can do all those. We can add many experimental data. We can calculate many descriptor on the columns, and then we can check which descriptor fits better. Okay, so all those things can be done with this particular software. Okay, so we can have activity equal to A plus A naught plus A1 molecular volume, or activity equal to A naught plus A1 dipole, or we can even have activity equal to A naught plus A1. Like I showed you, 3 descriptor models, so everything can be incorporated also. We can have 1 descriptor model, 2 descriptor model, 3 descriptor model. More data points I have, more descriptor models can be generated. Okay, with this particular tool, it is called the build QSAR. Okay, let's look at some more examples of this. Okay, so imagine I have a system like this, and these are called selective COX-2 inhibitors. And COX-2 is an enzyme in the prostaglandin pathway, okay, which leads to inflammation. So there are many drugs in the market. I've been showing you these inflammatory Alidicoxib. We saw the same thing in our pharmacophore also. So these molecules are reported as selective COX-2 inhibitors. So I've taken these are selective COX-2 inhibitors, whereas nimesulide, if you see, is not a selective COX-2 inhibitor. It's a general with no specific target. That is why nimesulide has lower activity. You can see here, nimesulide has low activity, whereas other molecules have high activity. But I have also taken that. We can try to develop activity is known. You can see these 5 drugs. Activity is given. Okay, so I have collected the activity of these molecules. So can I develop a QSAR? So what I have to do is, for example, I can get the so for example, I can use ChemDes, then I can get the SMILES notation for the structure from zinc, copy in ChemDes, and then calculate some descriptors for calculate some 200, 300 descriptors for each one of these molecules, put them in Excel, and put the activities also, and then see which descriptor correlates well with the activity, and maybe we can make one single descriptor model. Like I said, with 5 data points, it's always you should not go for a very large descriptor. 2 descriptors is not a good idea. Okay, so we will do that. That is how the workflow happens. So I'll go to first. I will go to zinc and database. I need the SMILES notation for this. Then I can copy it into okay, so we will look at each one of these molecules. Celecoxib, for example, um, celecoxib. And this is the structure of celecoxib. This is a selective COX-2 inhibitor, which is currently in the market. So I can copy this SMILES notation, go to ChemDes. So I'm looking at the descriptors given in ChemDes. Say it's got quite a lot of okay, ChemDes. Okay, so I can say chemistry descriptors. Okay, here I can copy the smiles notation for silicoxib. There are many descriptors, but I'm just calculating. So it's calculated lots of descriptors, almost you can see here. I'm scrolling. So it's called calculate a lot of descriptors. Now I can download that into Excel, because later on I want to get these descriptors for all these 5 molecules. Then I will see which descriptor correlates with the activity. So I'm going to do that. So I will download that in Excel. So I have downloaded that. Yeah, so you can see here a descriptor value. Some of them are zeros, some of these numbers. So if you want to know what these descriptors are meant, you can identify things like volume or surface area or log p, but there are many descriptors which are related to geometric parameters, graph theory. So you have to go to help of ChemDes or even some background literature to identify. Okay, some of the descriptors are very complicated to state simply, understand in a very simple way. Okay, they are slightly more complicated to understand. Okay, so I got for one molecule. Okay, so similarly we can get for other molecules also the same way. Okay, so like that we can get for, now I got from Celebrex or Silicoxib. Similarly, I can get for all of them, Alicoxib, DUP697, for example. If I put DUP697, I'll get the smiles notation. Okay, this is DUP697. So DUP697, I got the smiles notation. Okay, I can see that. I can put that here, and then I can get the descriptor information. Okay. Okay, so I got, so again I can download it in as a Excel file. Like that I can keep doing for all the 5 molecules. Okay. Okay, I put all of them, all the descriptors for all the 5 molecules calculated from ChemDes, and then I can put the activity. These are the activities which are experimental activities reported in literature. Okay, so okay, and that's what I have done here. Make it simple. okay, using ChemDes descriptor. So I have 5 molecules, DUT697, valedicoxib, silicoxib, roficoxib, and nimesulide. Nimesulide has the lowest activity, sorry. So the 5 activities are put here. IC50. So the 5 activities are put here in this column, okay, for all the 5 compounds. And then all the descriptors are put one below the other. So a lot of descriptors you can see here, sorry, down, which I calculated from ChemDes. Like I said, you need to go to the help of the ChemDes to find out the explanation of these descriptors. Some descriptors is very simple to understand, polar surface area or volume or surface area or number of hydrogen bond donors, log P, log S, and all that. But there are many descriptors which you will not understand straight away, which are calculated. So as you can see in this column, so many descriptors are there. Okay, more than 200 and odd descriptors. Activity is put in this column, the top row. And then what I do is I try to find, just like in the previous case, correlation between this descriptors here and the activity here, and then correlation with this descriptor and the activity. Like that I keep on doing and see which descriptor matches well. Okay, some of them. Okay, so don't bother about this div, because the whole thing is 0, 0, so that's why it's not giving a number. So if you look at this one, this particular descriptor and activity is correlating with the 0.23, which is very low, and this descriptor is correlating 0.76, and then we have 0.92, some very good numbers, and then like that, each descriptor has correlation with the activity. That is, this is this top row, giving different correlation. Okay, so as I go down, you can see there is one descriptor, okay, which is giving 0.98, which is very good. That's why I have marked it in red color. Okay, this descriptor has the best correlation with the activity. Okay, these 5 points has the best correlation with the activity. Okay, this is the descriptor, this is the activity. Okay, so you can even draw a graph and see how it is. So the descriptor is your x or the independent variable, and your activity is y, and that's the dependent variable. So don't forget that, and that's in statistics term. Okay, and the correlation is very good, 0.98, sorry, 0.96, I think. Yeah, 0.985. So it's a fantastic correlation we have. So you can see as the descriptor is increasing, activity is also increasing. It's a very good 0.98 is a fantastic thing to have. trend line. So for these 5 data points, we got a one descriptor model. The descriptor is the X, Y is your activity, R square comes out 0.97. It's very, very difficult in experimental situation to get such fantastic R square. Okay, so but it's a very good one descriptor model which describes our problem. Of these 5 anti-inflammatory drugs, but selective COX-2 inflammatory drugs, not any anti-inflammatory, but selective COX-2 inhibitors. Okay, these drugs are in the market. These 4 are in the market. This is not selective. Nimesulide is not selective, but the other 3 are in the market. They are called selective COX-2 inhibitors, and the DUP 697 is in the clinical trials. So the activity data is reported in the literature through experimental work which has been done by somebody. So what I did was I calculated many descriptors using, say, ChemDes, which calculates many descriptors, and then I did a correlation coefficient, and I found this particular descriptor has a correlation of 0.985, which is excellent. Will not get such very high numbers. So when I plot, you can see that at x-axis this is the descriptor, y-axis is the activity, and the QSAR is here. Okay, y equal to 11.2 into that particular descriptor. Okay, so R square is also very good. So this is an excellent model to look at. So if I have a new molecule I want to design for selective cyclooxygenase 2, what do? I calculate this particular descriptor using ChemDes. Then I can substitute in this equation of y equal to 11.2x minus, and then see what is the activity. If the activity looks better, much higher, say, then I can consider that as a possible candidate. If the activity doesn't look good, then I will not consider. And later on, of course, I need to check for ADME, drug likeness, bioavailability using Swiss ADME type things. So this is how we can do a QSAR based drug design. Okay, so what we did was we have known molecules with reported activity from the literature. Then we calculate the descriptors using different softwares there. I showed you which can calculate descriptors, and then we have the activity, that is the y or the dependent variable, and the descriptors or the x or the independent variables. Then we can look at their correlation, and we can select the descriptor which correlates best. We can develop one descriptor model. If I have, say, 10 data points, then I can even develop a 2 descriptor model. I can select 2 descriptors which are correlated with the y, that is the activity, and then I can make a 2 descriptor model. I can use the build QSAR model. But one important point is those 2 descriptors should not be cross-correlated. That's important, which I mentioned that like height and weight could be cross-correlated. So we should not have models which contains both height and weight of a person as x's, because tall persons could be much heavier than short persons. So there could be a close correlation. Similarly, surface area and volume could be correlated. So bigger, higher volume molecules will generally have higher surface area. So I will not have both surface area and volume in my descriptor QSAR. Like that, So if I want to go for 2 descriptor or 3 descriptor, number 1, I should have enough data points. Number 2, they should not be cross-correlated. Okay, so this is how the workflow for the QSAR looks like. Okay. So the main challenge is getting the experimental activity data, number 1. The second challenge is which descriptor to select. That is number 2. Like I've been talking about that example before. We can say tall persons can be good basketball player. We can say heavy persons could be good weightlifters. But if I want to know which descriptor describes the IQ of a person, we don't know, right? So we are lost. Same thing can happen in in activity also. We don't know which descriptor describes a particular, say, some anti-cancer activity or some tumor activity or some neuronal activity. So we may be taking the wrong descriptor. So if I want to develop, if I want to look at descriptor for an IQ based, we won't know. We don't know what are the pharmacophores for a person, for somebody to be judged as person with high IQ or low IQ. We cannot. Okay, same thing can happen in this also, in QSAR also. We will not be knowing which descriptor to select. So we may be selecting wrong descriptors, or we will not find any descriptors at all. That is also possible. Okay, so there are some problems, issues one needs to know, and we also should have a good knowledge about regression and statistics, because QSAR involves a lot of statistical knowledge. That is why many people will not use QSAR. They will stop with pharmacophore based modeling and then stop, because you need to have a lot of knowledge about statistics. We need to calculate our many parameters to see how good the fit is. Here in this say Excel, it's just giving R square, but there are many statistics which needs to be calculated to know how good the model fit is, how good the prediction is. I think, like I said, R square adjusted, R square predicted, Q square cross validated, R square bootstrap, R square F value. So many things are there actually, which tells you how good this fit is, and so that for that you need to have a good knowledge about statistics. Okay, so this is how the workflow for QSAR looks like, and you also saw the workflow. But ultimately, of course, we need to do the filters. We need to look at whether the molecule which shows theoretically good activity satisfies Lipinski's rule, Muge rule, Weber rule, ligand rule, bioavailability rule, blood-brain barrier penetrations, total polar surface area, log P. So all these should be satisfied. Otherwise, then that's not a good candidate. So simultaneously, we combine the ligand-based design, which I showed you in the left-hand side, with filters. But these filters we have to anyway use, even when you are doing a target-based design, that is docking-based design also. We need to use these filters to finally eliminate candidates which may have poor drug likeness type of rules, actually. Okay. There are many rules of thumb which one has to follow when you are using QSAR. Okay, so get molecular structures from Zing. Then we use Swiss ADME or ChemDesk or ADME-T or 3-ADME-T to get descriptors. So if I don't have the structures, yesterday I showed you Marvin. So we can draw the structure on Marvin. We can get the 3D confirmations also, and then go ahead getting descriptors, and then you can develop the models either using Excel or build a QSAR. There are many commercial softwares are there, and free softwares are also there, so we can use many of them. Okay, here I'm only focusing on free softwares only, and develop the models. Okay, points to note. So with 5 data points, develop only one descriptor model. Don't go for 2 descriptor models. Okay, activity should be equal to A plus B descriptor 1. It's not a good idea to make activity equal to A plus B descriptor 1 plus C descriptor 2. It's not a good idea. Okay. If you have about 8 data points or above, then yes, you can go for 2 descriptor models. Okay, then there is one important thing which I have not mentioned, but I will mention it now. Training set and validation data set. So suppose I get 10 experimental data points from literature, activity points. I will not use all the 10 points to make my regression equation. That's not a good idea. So I use only 80% of the points to make a regression equation. That means I will use only 8. 2 points I will keep it aside, only 8. And then with that equation, I will try to predict the activity of those 2 points. I already know the activity and see how good the prediction is, because ultimately QSAR is not fitting the data but also predicting the data. That's very, very important. Okay, so it's not just fitting but also predicting. So for doing that, what we do is we take 80% for training the data, that is getting the regression. 20% you keep it aside, and with whatever equation you got, try to predict for that remaining points. Okay, that's what we have to do in QSAR to see how good its prediction is. So we don't use all the data points for training. Okay, so it's called training set. Another is called test set or validation set. Okay, that's very important. So in my problem, which I showed you, the volume problem, I had 5 experiments. I should not use all the 5 to make my model. It's wrong. I should make 4 to make the model, and then I will try to predict for the 5th point and see how good the fitting is, how good the prediction is. Because sometimes fitting may be very good, prediction may be very bad. Then that model is not good. Okay, so that is why it is called validation set, validation data points. Okay, and then there are a lot of statistics also there. Okay, so this training and validation is extremely important when we consider. Okay, so in this problem, if you remember, we took all the 5 points and made our model. Okay, that's not a good idea at all. We should take 4 points, make a model, and then try to predict for the 5th point and see how good the prediction is. Okay, so let's try that. We'll take this problem and go to the next worksheet. Okay, imagine 80-20 is always true. Training 80%, 20% should be validation or test set. So I will not use all the 5 data points. I will use only 4. So I will get a model, and then with that model, I try to predict for the 5th point. That's very, very important. Okay, so we know volume is a good model. So what do we do? Insert data points. Select data, add X value. So here I'm not taking all 5. I'm taking only the 4. Okay, only the 4. See this, only the 4. Okay, I've taken only the 4. Top 4 points. I now will make a model. So I'll say add trend line, display R square. So this is my model with only the top 4 points. See this? There will be slight difference between this model and the other model where I took all the 5 points. Look at this. This has got minus 0.0, sorry, plus 0.0117, minus 2.103, whereas the other one minus, sorry, 0.0117 minus 2.0254. So some difference will be there in the equations also, because I have taken only 4 points in this particular case, whereas in the previous case we took 5 points. So we see this. Now I will try to predict for the 5th point. Okay, because I have not taken that in the model. So I will use this equation equal to 0.0117 star this volume, because this point I have not predicted. So I am going to predict using this model minus 2.103, 2.103, and see what is the activity it's predicting. So you see, it's predicting activity as 2.09, whereas the real activity is 2.55. Understand? So model fitting is very good, nicely. If you look at the previous graph, if I took all the 5 points, so nice. R square is 0.92. Here also, if I put R square is 0.94. Okay, it's fitting the 4 points, but the fifth point it is trying to predict, it's not really good. Instead of 2.55, it's predicting 2.09. So the predictive capability of this model is not very good. The fitting capability is good. That is why this is a very, very important point we all need to keep in mind when we are developing QSAR. Okay, when we are developing QSARs, this particular point is very, very, very important, because QSAR is not only fitting but also predicting. Okay, so the prediction, if I take only the top 4 if I take only the top 4 and try to predict the fifth one, model is good. So what I can do, I can think of some other 4 data points, try to predict. In this case, I neglected the last point and try to predict. I can try to neglect some other point and then try to predict. Like that I can have to do, because ultimately the predictive capability of the model is very, very important. Not only fitting but also predictive capability. I think if I neglect second point, it comes out good. Okay, remember, so I can, instead of some other fifth point neglecting, I can think of neglecting some other point. So I can say, I can neglect the second point. So this is the second point. Okay, so I have neglected the second point. Select data, add x value is so now here I have neglected the second point with respect to that, and they can remain in 4 points. Okay, in this problem, see, in this first problem, I took all the 5 points. In the second case, I took only the 4 points, top 4 points, and made a model, tried to predict the last point. In this case, I rearranged so that the second point, I put it here. So I neglected that and tried to predict. Each time I'll get a different model, of course. Okay, so I'll get slightly different model in each case. If you look at the constant term, maybe so I am predicting. Now the second point, let us see how good the model is. 0.0. This one is same. The slope is same in all cases, but there is slight difference in the intercept in each one of them. Okay. Okay, you see, this is a very good model. Good model with respect to prediction. It has predicted 1.84. Okay, so if I leave the fifth point and take the top 4 point, the model I get has poor predictive capability. If I leave the second point, you saw I removed the second point, put it at the bottom, and took only first, third, fourth, fifth point, and then develop a model. It's got a good predictive capability also. So ultimately, that's a very, very important point we need to keep in mind. Actually, the predictive capability of the model, not only the fitting of the model, but the predictive capability of the model. You can see this. Training and test or validate, because QSAR is not only prediction. So not only fitting the data like a regression, but also the prediction. That's very, very important. So in QSAR, we need to do this. We need to take 80% of the data points and fit our model, and then try to predict the activity for the remaining 20%. In this particular example I showed you, 5 data points, 1 data point I did not use it, so I used only the top 4 data points, try to predict for the 5th data point. Unfortunately, although it looks the this one is good. Yeah, although the fitting is good, fitting, you can see nice fitting, but the prediction is bad. But when I remove the 2nd data point and use first, third, fourth, fifth, and then try to predict for the 2nd data point, the prediction is very good. Okay, 1.8 and 1.8. So you may have to do these type of studies also. So each leave the 20%. How do I select? I may select randomly some points, make a model, then try to predict for the left out points. See how good the prediction. Then I may take out randomly some point and leave it for validation, and then try to again predict for that. So like that, I need to do many times, and then see how good not only my fitting but also my prediction. Okay, that's very, very important in QSAR. So depending upon how good the prediction is, we will decide that this particular model has good fitting and prediction, both. So in this particular example, we saw when I leave out the 2nd point for validation, I get a good model which has good predictive capability. So I know before because I have done this problem. Otherwise, if you don't know, you may have to try leaving out 5th point, then 4th point, leave out, then do, then 3rd point, leave out, do, leave the 1st point, leave out and do. Like that, we need to do 5 times, and then we may end up with the model. So if you have to leave many points, then you may have to do many times in a random fashion. Finally, you get a model which has got good fitting. That means all the data points in the training set are fitted, as well as its predictive capability is also equally good. Okay, that is the end of QSAR. That is a model which has got good predictive capability also. And that particular model, you take it for your for predicting activity of new unknown structures. Knowing the structure, if I don't know the activity, I will use it to predict the activity for the new unknown structures. Okay, that's what is it. Ultimately, this prediction is a very important point. It's not only fitting, but also prediction. So we have many rules of thumb, we call it. So always try to follow those rules of thumb. So if I have 5 data points, don't go beyond the 1 descriptor model. If you have 10 data points, you can go for 2 descriptor model. Then divide your data set into training and validation data set. Always do that. Don't take all the data and try to fit a model. 20% you keep it as so if you have 10 data points, I would say 2 data will become validation, so you'll have 8 data points only. So there we can think of 1 descriptor or 2 descriptor model. Then try to predict those data points left out and see how good the prediction is. So if that is not good, take some other 2 data points as a validation. Again, make a model with the remaining 8. Again, try to predict those 2. Like that, we may have to do many, many times until we get a good model which fits well as well as it predicts well. Okay? That is what is the QSAR is all about. Ultimately, that is what gives us a good QSAR, which gives you good training as well as good prediction. There are many statistical terminologies which come into QSAR, like R square, adjusted R square predicted, Q square, cross validated R square, bootstrap. So we need to calculate all these. There are softwares which can do, and then based on those, we say this model is good, and this model has good predictive capability, this model has good fitting capabilities, and so on. And that's how we end up with a good model which can do both these types of activities. So in QSAR, generally we can use Excel like software if we have the one parameter model or descriptor model. And the one which I showed you, that's a free software build QSAR. It can do 2, 3, 4, 5 many descriptor models also. It's almost like, it looks like Excel, so it's easy. We can copy paste from Excel into this, and then descriptors we can calculate from ChemDes, or we can calculate from OChem, or we can calculate from ADMET. There are many softwares which can give lots of descriptors, and we can use many of them. Yesterday I showed you some things like that. OChem, ChemDes. There is another software called eDragon. So all these can calculate descriptors. There is a eDragon, Swiss ADME gives, ChemDes gives, OChem gives, TADME. So all these gives many descriptors. So if you want to, you can have thousands of descriptors put into. Here I showed you that for the COX2 about 300, 400 descriptors, but we can put thousands of descriptors and then see which descriptors fits the data with the training set, and which gives you a good validation or prediction also. So there are commercial softwares also available. My focus of this is not to talk about commercial software. Our focus is more on the free software. Okay, so this build QSR is what I showed you some time back. Okay, so that completes topic of QSAR. So if there are any questions, I'll be pleased to answer.
Sir, good afternoon, sir.
Good afternoon.
Sir, QSR model, why we should always take experimentally generated? We cannot use the theoretical one, sir. Like we cannot use the docking scores.
No. Theoretically is what you are predicting, but to start with, we need experimental data, right? Always experimental data is 100% correct. So from experimental, we develop model, and then we will try to predict.
No, with structure can we? No, with structure can we do like docking scores, or we can develop an QSAR model with a docking score or something like that, sir?
Oh, okay. You can do that, but that is based on docking base. That is target base. Here, I am not talking about. Please understand. No, I'm not talking anything about target. So far, past 2 days, I have been talking only about ligand based. But if you have docking scores, you can talk. But still, that is not a correct one, because ultimately docking score is not exactly matching with the experimental. So you should start with experimental data. People do binding energy versus activity, but again, you need some activity data to start with. Then how do you know your QSAR is perfect? Because we don't have any experimental validation in that, right?
Okay, sir. Okay, sir. Thank you.
So some experimental PIC 50 or percentage inhibition, ED 50 or LD 50, something like that. ED 50, LD 50 percentage inhibition, or some UV reduction. Some data will be nice to have. Because ultimately,
UV reduction also. UV reduction can also be used.
Yeah, so ultimately, whatever theoretical we do, ultimately experiment is the proof, right? Ultimately.
Sure.
So I have seen in case, although many times there is a difference. So finally, some experimental validation.
Yeah, we can use Gaussian to get a molecular descriptor. So Gaussian, or we can use Gauss.
Yeah, you can do that. Yeah.
Yes. Thank you.
Thanks.
Hello, sir. I have three questions, sir.
Sure.
Yeah. So first of all, how can we prevent non-specific binding of repurposed drugs?
Non-specific binding. So okay, so you are going into the target-based design. Okay, so far we have not talked about it. So basically, it depends on the binding to the site. So it is not that there will be only one site in a protein. There could be many pockets, right? So if you know the pocket characteristics, pocket has certain hydrophobic characteristic, hydrophilic characteristic, electrostatic characteristics. So if we know those characteristics, so we need to design the ligand so that it prevents going into that. So if it is a very hydrophobic pocket, no, I'm not talking about active site, hydrophobic pocket, which is not an active site. So don't have highly hydrophobic molecules. If you have hydrophilic, it will not go and bind to that. So that is how people design actually. So if you think a particular hydrogen bond donor is going to be interacting in a pocket which has got a lot of hydrogen bond acceptors, remove the hydrogen bond donors. Instead of OH, you convert it into OCH3 or CH3CO, like that, so that it will not go and bind. So based on the characteristics of those pockets which are not needed for binding, then you need to correspondingly design your ligand correspondingly.
Okay, sir. So and then how do we improve the bioavailability score? You were talking about it day before yesterday.
Okay, yesterday bioavailability is made up of many things. Number one, it should have water solubility, because we are talking about oral bioavailability. Don't forget oral. If it is given intravenously, that's a different story. Oral, first it has to dissolve in the GI, and then it gets absorbed across the GI, go to the bloodstream, and then there will be the cytochrome enzymes present in the liver, which degrades, and then there will be some absorption in the tissues, and then finally it reaches the target site. So the bioavailability is ratio of how much is reaching at the target site divided by how much drug you give into 100. So 55%, 40%, 30%, and so on. Okay.
Yes,
so if you know what is the problem, suppose its GI absorption is poor because it's very hydrophilic, then hydrophilic means it may be having OH or NH2 and all that. So we add hydrophobic groups and reduce and make it more lipophilic. Okay. Or if it is, suppose you have ester bonds are degraded by lipases present, esterases present. So some of the drugs can get degraded. So you try to make the ester into amide bond. Amide bonds are more difficult to degrade, unlike ester bonds are easiest to degrade in the inside the system. So you modify. So exactly, if we know, for example, you take Taxol. You all know what is Taxol. Taxol is a anti-cancer drug used in many uterine cancer, so many cancers. Okay, it's a natural product found from a tree called yew tree. The Taxol had very good activity, but the original Taxol had very poor bioavailability, 18%. Okay, because its water solubility was very, very low. So what they did was, second generation Taxol, they made lots of OH groups they put in, so the bioavailability improved to 20%. Then third generation Taxol, they made it into salt. Salt means potassium salt, like that. As you know, salts are highly soluble in water. Now the bioavailability increased to almost 40%. So you see, those are the strategies which people follow. And number two, if the molecule is very crystalline, solubility is poor. So make it more amorphous. So bioavailability can be improved. If it is very like that, so if they make it more amorphous, bioavailability can be improved. If it is more hydrophobic, try to reduce the hydrophobicity. If there are ester bonds, change the ester bonds to amide bond. So if it is a PGB-FLEX substrate, then add bulky groups into that, so that you reduce the PGB-FLEX conditions. So there are so many things. So the example of Taxol is a very easy example. Another thing which you can think of is targeted drug design. So you can have encapsulate so that it nicely penetrates the GI and reach the bloodstream. We can encapsulate so that it doesn't get degraded inside by enzyme. So exactly, if you know why the bioavailability is low, we can design or modify correspondingly to improve the bioavailability. If the solubility is poor, very, very poor, for example, oil, people also get injected with oils. Oils have a lot of as a therapy, so they may go into intravenous. So if the bioavailability is very low, but still you have to have the drug, then they go into intravenous. So many chemotherapies are given intravenous, right? So it's not through oral route, it's given through intravenous or intraperitoneal. So if definitely it has to be given and there is no way of modifying, then they go into intravenous type of situations. Okay, so or we have encapsulated systems, improve the bioavailability. If it is a drug which is going to get degraded at pH equal to 2, which is your stomach, they may have gelatin like coating. which will
Yes,
reduce the degradation at pH equal to 2. So exactly, if they know, they can they do that. So many modifications are done. Otherwise, worst comes to us, it will become intravenous or intraperitoneal. For example, if you take insulin cannot be ingested through oral route because
orally. Yes, sir.
it's a big molecule, a macromolecule. It will get degraded pH, so it's given intravenous. So that is the ultimate. But nobody likes injections, intravenous, intraperitoneal. Everybody likes oral route. So generally, designs are made through oral conditions.
Okay, okay, sir. So, and one last question, sir.
Yeah, sure.
Sir, you were only using linear models in the QSAR descriptor activity relationship. We can also use nonlinear models, right?
Oh yeah, you can use second order, third order, but the number of data points have to be high. So, like I keep saying, 5 data points have only one descriptor model. Y equal to m into descriptor 1 plus plus c. If you have 8, 9, 10 points, you can use log p square plus log p also. Yes, you can do that. You can look at that type of model. There are situations where some molecules have good absorption at optimum log p, and the absorption changes when the log p is increased or decreased. So that is like a second order relationship. Okay, so you can have, yes, depending upon data points, yes, you can have. And if you know the science behind it, if it is important, log p is important, and there is an optimum log p. Sometimes we do antibacterial experiments. We do know at pH certain condition it grows well, at some other conditions or above or below it doesn't grow. So there is a parabolic relation with pH, right? So like that, we can have parabolic models, that is second order models. Yes, the data points are very important. That's what I have been emphasizing today.
Yes, sir. Yes, sir. That's all, sir. Thank you so much, sir.
Thank you.
Good afternoon, sir.
Yeah, good afternoon.
Sir, how do you select these 5 anti-inflammatory drugs? Is there any specific reason to select these drugs, sir?
No, these are anti-inflammatory COX-2 inhibitors. They are in market for selective COX-2 inhibitors. Bextra, Vioxx, Celebrex, Rofecoxib, DUP697. They are all drugs available in the market, sold for selective COX-2 inhibition. COX-2 is an enzyme found in prostaglandin pathway, which is involved in pain, inflammation, arthritis. So these are drugs available in the market. So I selected a practical example. Like nimesulide is also a drug, but it's not selective COX-2. It is used for pain and all that, but it's not selective COX-2. So it goes and binds to many other enzymes also. Okay, so these are all practical. This is a practical example which I have selected.
Okay, sir. Thank you, sir.
Thank you.
Thank you so much, sir.
Thank you. Okay. Okay, then we will sign off. Tomorrow we will talk about the target-based design,
Okay, sir.
where we have the 3D structure of the target. Okay. Thank you.
Thank you, sir.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you.
Participants are requested to fill your attendance link and submit the feedback. Those who are completed can leave.
Yeah.
Thank you, sir.